Hello everyone, welcome to this video which is on lecture 10 entitled The Formation of Planetary Systems. In this video we're going to talk about how planetary systems form. In particular we're going to mention our solar system, but we believe that this theory that I'm going to present to you regarding how our solar system forms can be applied to other solar systems. I will also tell you how we come to think of this theory as being valid, how we validate our theories, because the first question that might come to your mind when we're talking about the formation of our solar system is that this must have happened a long time ago. And the answer to the question of how we know that this model is valid has to do with other solar systems as well. If we want to understand how our solar system forms, we should first look at some of its characteristics and see if we can compile a list, particularly of characteristics that seem odd or connected together in some way. Let's talk about these four characteristics and then try to understand how we can put these together in a cohesive way to come up with an explanation for how they can be simultaneously true. The first is that each planet revolves around the Sun in separate and nearly circular orbits. All of these orbits lie in the same plane. I will show you an animation of the solar system in just a moment. Actually, it's the same animation I showed in a previous video for a separate purpose. But we already know that all the planets orbit in separate orbits, that they're all, with the exception of Mercury, very circular. Not perfectly circular, but pretty close. And something I did mention is that each planet orbits in a counterclockwise direction as observed from above Earth's North Pole. And I mentioned just earlier that they all lie in the same plane. This is a big clue. The solar system is like a thin pancake. The planets and the gases, the small solar system bodies, etc., are arranged in this roughly circular pattern that's very thin compared to its diameter. In addition, we know that the oldest meteorites are about 4.6 billion years old. We don't find any older than that. We also know that the planets and the moons are differentiated. This means that the interiors of the planets tend to be hotter and denser than the exteriors. Let's use the Earth as an example because this is the planet that we understand best. Since we live here, we know that the center of the Earth is very dense and very hot. It has a temperature roughly that of the surface of the Sun, actually. And the crust of the Earth is far less dense and, of course, far less hot. The solar system is also differentiated, which means that there are rocky interior planets and gaseous outer planets. In this context, differentiated means that there are different molecules that tended to form planets in different parts of the solar system. Near the Sun, we have metallic rocky planets like Mercury, Mercury, which is highly metallic, and Earth, Venus, Mars, all rocky planets, although those three planets are less metallic than Mercury. And then, of course, we have the gaseous planets, and those are all outer planets. We don't have a mixing of gaseous and rocky planets. We don't have a rocky planet as the eighth planet, and then a gaseous planet as the first planet with respect to the distance from the Sun. There are other things we could talk about, but let's stick with these four. Let's see if we can put together an explanation that explains all four of these bullet points. First, before we get into what we call nebular theory, I want to show you the animation that I referenced earlier. This is an animation of the solar system. You can see here, if I just pause it and move it around, that the solar system is a plane. You can think of it as sort of like a pancake. It's hard for me to draw on this. I don't think I can, but the yellowish orbit that is angled with respect to the plane is Pluto's orbit. So many of the asteroids and dwarf planets like Pluto don't orbit exactly in the same plane, but all of the 8 planets whose orbits are in blue orbit in the same plane, with the sun at the center. The solar system is therefore a highly ordered object. And this leads us to the basic idea behind what we call nebular theory. The idea is that the sun and the planets have a common origin. They form together. This would make sense because, as I just said, the solar system is an ordered object. We don't have planets orbiting in random orbits. They all orbit in the same plane, and all of their orbits are very close to circular, with Mercury being somewhat of an exception. The nebular hypothesis actually is rather old. It comes really from the 18th century, but it's been modified over time because our understanding of the solar system has improved a lot since the 18th century, as you might guess. And the idea is that the solar system evolved out of a nebula, which is a large cloud of interstellar gas and dust. The idea is that this nebula, which before the formation of the solar system, before the formation of the solar system was much larger than the solar system, eventually contracted under its own gravity, and as it contracted, it began to spin faster and faster, creating the movement of the planets eventually around the sun, the orbits of the planets, and as it contracted, it formed a disk, which is our solar system. And that's what I'm saying down here in this last blurb. As the solar system began to form from this nebula which contracted under its own gravity, it formed what we call a protoplanetary disk. We have pictures of protoplanetary disks, actually. This now gets me to what I was saying earlier with regard to how we know that this is valid. This seems to fit the facts, but what we want to do is try to be able to falsify our model. We'd like to look out into the universe and find solar systems that are forming and be able to compare the nebular theory to how solar systems that are currently forming actually look. And we can do this because it turns out that although it takes a long time for solar systems to form, there are many that are currently forming. And so by examining all of these different protoplanetary disks, solar systems that are in the process of formation, we can look at snapshots of this process in different points in time. This is a protoplanetary disk as conceived by an artist. The level of detail here is too great to be a real picture, but this is a real protoplanetary disk. And this is ultimately how we validate our nebular theory. We compare the stages that we would predict for solar system formation to actual examples that we can find in the universe. Let's talk about why contracting objects spin faster. I mentioned that the basic idea is that we have a very large cloud of gas and dust, which is called a nebula. And this contracts under its own gravity and then begins to spin faster. Let's leave the contracting under its own gravity aside. That process, or the reasons behind that, are a little bit tricky. Maybe I can just give you a brief overview. I'm going to try to draw here. So this is a giant cloud of gas and dust. In any cloud of gas and dust, there are going to be some regions which have a higher density than other regions. The cloud is not going to be perfectly evenly distributed. Just as if you throw a bunch of M&Ms on the floor, there's going to be a buildup somewhere on the floor, very likely. They're not going to distribute themselves perfectly evenly. So there might be a region, this is not color-coded, I'm just choosing random colors. There might be a region that has a relatively high density, and that region may end up contracting to form a disk. That's the essential idea. And the contraction is going to occur because if a piece of the nebula has a relatively high density, then the gravitational pull will be larger in that area. But let's leave that aside and talk about why, as these nebulae contract, they spin faster. This turns out to be a general concept in physics, and it's related to something that we call angular momentum and the conservation of angular momentum. Let's talk about a merry-go-round. Here I have a picture of a merry-go-round, kind of an odd picture with cartoon characters, but the idea is that if you have a merry-go-round which is spinning around, as they tend to do, the merry-go-round will have a large angular momentum. What this means in practice is that it's very hard, relatively hard, to stop the merry-go-round. If an object is spinning with a large angular momentum, you have to apply large forces to stop the object. So you can think of angular momentum as the tendency of an object to keep rotating once it's rotating, or the resistance of an object to get rotating if it's not rotating. And what that means is that you wouldn't reach out. Let's say that the engine has stopped. There's a merry-go-round going around pretty fast, but the engine is cut, but it's just rotating on its own via its own momentum. You wouldn't reach out and grab one of the ponies to stop the merry-go-round. That would be dangerous because very likely you would get hurt. The merry-go-round has such a large angular momentum, you can't just reach out and grab it and stop it. It would bring you with it, which probably would hurt you. So we all know that, and the reason is because it's hard to stop it. On the other hand, if you spin a top on a table, you could easily reach out and grab the top and stop it and pull it toward you. There's no danger in that. And that's because the little top only has a little angular momentum. Let's talk about where angular momentum comes from. How come the merry-go-round has a larger angular momentum than the little top on the table? The reason is that the merry-go-round has a larger moment of inertia. Let's talk about that first. The merry-go-round might not be spinning very quickly. It might spin once every 5 or 6 seconds or something like that. That's probably too fast. Obviously, you don't want them to spin a few times a second, otherwise it would be dangerous. On the other hand, if you take a top and you spin it on a table, it's probably spinning around multiple times per second. And so therefore, the speed at which something rotates is not the only factor in determining its angular momentum. The merry-go-round has a larger angular momentum because it has a greater mass than the top, obviously. Merry-go-round weighs thousands of pounds, probably. And that mass is actually distributed away from the center of rotation. The mass is physically separated from the center of rotation, which in this case is going to be this pole in the center. The merry-go-round spins from the center, obviously. And this gives rise to what we call the moment of inertia. The moment of inertia is a property of an object. All objects have moment of inertia, which is a measure of the amount of mass an object has, and also the separation of that mass from the center of rotation. Now, different parts of the object will be separated different distances from the center of rotation. If you take an object that's at the edge here in red, it will be separated by a larger distance from the center pole than if you take something right next to the pole. But the idea is that to compute the moment of inertia, we'll average over all these distances. Now in this course, we're not going to be computing moment of inertia. We just need to understand it in principle. If we take a lot of this mass in the merry-go-round and we bring it toward the outside, we will increase the moment of inertia even if the total mass doesn't change, because we're increasing the distance between the molecules that make up the merry-go-round and the center of rotation, in this case the center of the merry-go-round. The other thing that affects angular momentum is probably more obvious, and that's the angular velocity. This is the number of rotations per second. So in other words, if the merry-go-round is spinning at a frequency of 2 rotations per second, it's harder to stop than if it's rotating at 1 rotation per second. I think that's pretty intuitive. Same with the top, although with the top it's so easy to stop it, you hardly notice anything. If I multiply these two things together, angular velocity times moment of inertia, then I will get angular momentum. As I said, we're not going to be calculating anything. I just want you to understand this in concept, in principle. And what's the basic principle here? It is that if the moment of inertia of an object increases, let's say, the angular velocity must decrease, and vice versa. The point here is that angular momentum is conserved. So far, I've just talked about what angular momentum is and how to, in principle, calculate it. But the main point here is that now let's go back to astronomy and stop talking about merry-go-rounds. For a giant collection of gas and dust, the angular momentum is conserved because there are no outside forces. Angular momentum will be conserved if you have a system that is what we call closed, meaning nothing outside of the system is coming in and applying forces. A giant cloud of gas and dust in space is like that. It will collapse under its own gravity, let's say, it could, and then if the moment of inertia increases, because angular momentum must be constant, the angular velocity will decrease. As this goes up, this goes down. Now what actually happens, that's true, what actually happens in a contracted nebula is that the moment of inertia goes down and the angular velocity goes up. But both of these scenarios are in principle correct. But I will show you why the moment of inertia for a contracting nebula of gas and dust would decrease. So let's keep that in mind. This is the explanation for why contracting objects spin faster. I actually want to... Oh, okay, I have a whole slide on this actually. All right, everything I wrote here is true, but I actually have a whole slide with this, so I want to show you this slide first, and then I'm going to go over an example. That's what I was just thinking about. I was just saying all of this earlier. The conservation of angular momentum says that unless some outside force acts on an object to alter the rotation, the angular momentum of an object or objects will remain constant. That means that the moment of inertia times the angular velocity is the angular momentum, and that remains constant. It turns out that as a nebula contracts, the moment of inertia decreases. This then increases the angular velocity, because as moment of inertia goes down, angular velocity goes up. And I want you to think about this in just a mathematical way, because when you multiply these two things, you get a constant. And the same would be true if you took moment of inertia and increased it, angular velocity would go down. That's the point I was just making earlier. Now let's talk about why the moment of inertia of a contracting nebula, generally speaking, any contracting object will go down. What's the idea behind that? The basic idea is that if you have an object which is contracting, the mass stays the same, but the distance between the molecules and the center of rotation will decrease. We can understand this by looking at these two objects here. Let's say these objects have exactly the same mass. These are cylinders. They're identical in every way. In fact, we could even think of this as one cylinder. We take the cylinder and we place it vertically, and then we have it rotate about its vertical axis. So imagine taking your pen and holding it vertically and then twisting the pen around and around while keeping it vertical. So just rotating the pen about the line that goes down the center of the pen vertically. And then you can take the pen and you can orient it horizontally in front of you, and then you can spin it about the axis that goes, the same axis that goes down vertically. So hold the pen in the center with two fingers and then spin it around. It's hard for me to describe this without showing you a video of this. But my point is that as you spin the pen around, in the second case here, the moment of inertia of the pen is going to be larger. Actually, I just want to be clear that the moment of inertia is a property of the object. The pen has a larger moment of inertia in this case, case number 2, than in case number 1, even if you're not spinning it. So even if you just hold the pen with 2 fingers horizontally, where the 2 fingers are holding the pen from the center, the moment of inertia, and you're not spinning the pen, just holding it, the moment of inertia of the pen is still larger. It has some value which you could compute, and that's a larger value than if you hold the pen vertically. But the point is that if you were to try to rotate the pen in the second case, it would be harder than in the first case. I think you can tell that if you rotate it with 2 fingers back and forth versus if you hold it horizontally, versus if you hold it vertically. Although with a pen, there's not much mass there, so it's hard to tell. But the point is the moment of inertia is larger in the second case than the first, even though these 2 objects are identical. And it's for the reason I just mentioned, because in the second case, there's a greater separation between the molecules of the pen and the center of rotation than in the first case. The same logic applies to nebulae. As nebulae contract, I just want to draw a picture actually. I'm going to talk about the tightrope walker in just a second. Now let's go back to our picture of a nebula that is contracting. This is a terrible depiction. I'm sorry, I can't draw anything, but anyway, this is a nebula here that I've drawn, this black blob, and it contracts under its own gravity and it becomes smaller. And as it contracts, the distance between the center of rotation and the gases that form the nebula decreases. I think you could see obviously the distance decreases because it becomes a tiny disk. Therefore, the moment of inertia of this object decreases. The moment of inertia here in, I'll call this case 1. Now case 1 and case 2 mean something different, but this is case 1, this is case 2. The moment of inertia is going to decrease substantially. It's like going from here to here. And as the moment of inertia decreases, the speed at which this object rotates increases. And I'm not doing justice to the scale here. The solar system is way smaller than the nebula that the part of the nebula that it came from. So the solar system and other solar systems contracted by huge amounts, not by a factor of just 2 or 3. Let's talk about tightrope walkers before we continue. Why do tightrope walkers carry long sticks? I know this doesn't seem to have anything to do with astronomy, but actually it does, because the reason for tightrope walkers using long sticks is conservation of angular momentum. The same principle that we use to explain the origin of the solar system. This is a picture of a very famous tightrope walker back when not many people did this kind of thing. And this, I think, is from the late 19th century, although I don't remember the date, I'm sorry to say. But here she's crossing a river. I also don't remember the river, I'm sorry. It's all escapes my memory. But anyway, this is a real picture. And you can see she's carrying a very long stick. The point is that if you're on a tightrope, you do not want to rotate. You're like a pen oriented vertically on a table. It's very hard to balance a pen on a table. And that's because if you balance a pen on a table, the pen will tend to rotate about the bottom of the pen. It will rotate so that the top of the pen will hit the table. We all know that. And the reason is that the moment of inertia of the pen with respect to the bottom of the pen, because the pen's going to rotate about the end of the pen, the part of the pen that's touching the table, is very large. And so there's other reasons actually too, but the moment of inertia of the pen is relatively large. And once the pen begins to rotate, it's very difficult to stop it from rotating. We can use this principle, but to have the opposite goal in the case of a long stick. You can hold a stick horizontally, and then as you begin to rotate, you can balance yourself very easily because you can just move the stick in the opposite direction in which you begin to rotate. So for example, suppose you didn't have a stick. You're like a pen oriented vertically. Once you begin to rotate, it's very difficult, to stop you from rotating. And of course, the whole point is to not rotate. So you can have a stick, and as you rotate a little to the left, because you're not walking, you're not walking in such a way where your weight is perfectly balanced. As you rotate to the left a little bit, in other words, fall to the left, you can orient the stick, so that the right part of the stick goes down. And therefore you can balance your rotation. And the reason why you use a long stick is because a long stick has a very large moment of inertia. So if you rotate the stick just a little bit, you will end up causing a very large change in angular momentum. Because remember, angular momentum is the angular velocity times the moment of inertia. If this tightrope walker here, or another one, had a very short stick, you'd have to rotate it really hard, really quickly, I should say, which wouldn't be very useful. In any case, I just wanted to connect astronomy to Earth physics. This is an important concept because ultimately this is how we understand the universe. We take experiments we can do on Earth, principles that we can articulate by doing experiments on Earth, and we can apply them to the cosmos. I want you to stop now and watch this video on why contracting objects spin faster. This is a video from NASA, and this person here is an engineer who's going to teach you angular momentum and from space. And you can tell he's in space here. It's much easier to do angular momentum experiments in space, as you will see if you watch this video. So please stop and watch this video. It's only about 3 or so minutes long. I have posted this to Blackboard near the same place where I posted the link to this video. Once you're done watching that video, please come back to this part of the lecture. Let's talk about Nebular Theory Part 2. So far, we've been trying to explain why the solar system is a small disk, small compared to a nebula, why it is flat like a pancake, and why the planets are orbiting all in the same direction. This is all explained by what's called the nebular theory. If you have a nebula which contracts, it will spin faster and faster. This will tend to produce a disk, sort of for the same reason that if you spin dough, it will produce a disk. If you take pizza dough in a ball and you spin it around really quickly, it will tend to flatten out the dough. The same principle applies to the solar system. This explains why the solar system is a flat disk and why all the planets are orbiting in the same direction, because this rotation came about for all the different parts of the solar system at the same time. One thing we haven't explained yet is why the gaseous planets form farther from the sun than the rocky planets. By the way, the nebular theory also explains why the planets have roughly circular orbits, because as something rotates faster and faster, the tendency is for it to rotate in a circle. I'm being a little bit imprecise with my language there, but I think that's intuitive, that the planets would orbit roughly in circles. But why do the gaseous planets not form close to the sun? This is what we call condensation theory, and the idea is that as the solar system formed, it formed together. The planets and the sun formed at around the same time. And as the sun began to form, we'll talk about how stars form a little bit later in this course, but the idea is that, I think you can tell intuitively the idea, the center of this solar system was the densest part, and it was collapsing under its own gravity. And as the center of the solar system collapsed under its own gravity, the very center of that object, which would have been a roughly spherical ball of gas, became very hot, and this became the sun. That's the basic picture. So as the sun began to form, the center of the solar system became quite hot. And the idea is that grains of dust, rock, silicate, ice, gases, etc., whatever was in the nebula, assist in the collapse of the nebula and create the protoplanetary disk. But the kinds of grains that predominated were different in different parts of the early solar system. I think it's intuitive that water, and especially ice and methane ice, etc., would not have been able to form and clump together in large quantities near the early sun, which is called a protostar, by the way. And so near the center of the solar system, you would not expect grains of ice to coagulate together, coagulate's not quite the word, but to accrete is actually the word, to accrete together to form a larger and larger object, namely a planet, because it was very hot. You would expect ice to accrete together to form a large object near the outer parts of the solar system where it was very cold. A nebula is very cold, generally speaking, unless there's a star nearby. A giant cloud of gas and dust in space is going to have a very low temperature. So it's very easy for ice to form unless there's a protostar that is forming in the center of the solar system, which is becoming very hot. So therefore, we would expect metallic and rocky grains to accrete together to form planets in the center of the solar system, near the center, and then we'd expect gases and ice and methane, etc., to methane's a gas, but I'm talking about extremely cold gases, ices, to accrete farther out. Okay, so this is essentially what I'm saying in this paragraph here. Only metallic and rocky grains could form near the sun, whereas icy grains were able to form farther from the sun. This is what I was trying to say, maybe more articulately. And this is referred to as a differentiation of the solar system. This is what we would expect if we had a star that formed, such as the sun, which formed roughly simultaneously with the formation of the planets. And this is validated by experiment, certainly in our own solar system. This is a graph of the differentiation of the solar system. This, along the vertical axis, is the temperature of the early solar system. And this is the distance from the sun, from the protostar. This would be the sun at 0. So you can see the temperature is very high. Near the sun, we have the rocky planets, namely metals, you would expect to form. This is Mercury. And then we have Venus and then Earth. For Earth, we have metals, but mostly rock. And then we have, outside of Earth and Mars, the terrestrial planets, we have Jupiter, where we would expect water ice and gases, and then eventually other kinds of ices. Let's talk about protoplanets. The formation of the planets was a very complicated process. Grains of various materials accreted together, eventually to form larger objects known as protoplanets, and then these, over time, gained other materials via collisions, etc., to form planets. And this process took about 100 million years. And at this point in the course, if we had a physical class, I would ask you to tell me, how would we know, do you think, that this took about 100 million years? And there are two basic answers to this question. One is that we come up with models, computerized models for these processes, and we can run these models using the physics that we have, and we can estimate the amount of time it would take. And we don't mean, by the way, that it would take exactly 100 million years, as opposed to 100 million years in one. We mean roughly 100 million years. Maybe, I'm not sure what the errors on this are, but maybe 90, 95, 100 million, 105 million, something like that. And excuse me, the second reason is that, as I mentioned earlier, we have snapshots of the formation of planetary systems, snapshots of this process occurring in different stages, because we can look out into the universe, actually mainly the galaxy, since that has the vast majority that we can see clearly, and we can see different protoplanetary systems in formation in different stages. So that's how we come to the conclusion that this takes about 100 million years. Let's talk about other planetary systems other than ours. Planets that orbit stars other than our sun are referred to as exoplanets. I showed you a picture of a real protoplanetary system earlier. We also know of many solar systems that have already formed. And therefore, we can find planets that orbit those stars. And as I said, these are known as exoplanets. And this is a very recent field because finding planets is very, very hard. Finding stars is hard enough, but stars emit far more light than planets do. I showed you a video earlier in the semester of the sun and the Earth to scale. This I showed, I think, during lecture 0, the introduction lecture. I had a slide in that lecture which depicted the 8 planets to scale. And I didn't have the sun there because the sun would be way too large for the slide. But I did show you a video from NASA of solar prominences, etc. And in that video there is a little picture of the Earth added to scale. And my point here is that planets are way smaller than stars. In addition, they're not nearly as hot. So therefore, the amount of light they emit is tremendously smaller than that of stars. Finding planets, therefore, is extremely hard. This is the point I'm trying to make. And it's only been since roughly the late 90s that we've been able to find really any exoplanets. However, we've been able to find tons of them. I'm sorry that I don't have the most updated numbers here. I forgot to update them. I apologize. I can put the update in a little blurb in the comment section when I upload this video to Blackboard. I'll put a comment near the link. But as of roughly this time last year, there were about 4,000 confirmed exoplanets and about 3,000 confirmed planetary systems. I'll talk a little bit about how we find exoplanets. But first, I just want to mention that one of the goals of finding different exoplanets is to find ones in particular that we think might be good for life, that we think might be habitable. And there's a rough guide to determining this, and this is pretty speculative because we haven't found life outside of our solar system, we think, with the possible exception of Venus, which is in dispute. So we could be off with this idea, but the idea behind the so-called habitable zone, which is one of the main principles behind the search for exoplanets that might be habitable, is that if a planet is too close to the star, it will be too hot. This would be like Mercury. Mercury is not habitable for many reasons, but one reason is that during the Mercury day, the surface of Mercury is way higher than the boiling point of water. Even if you had an atmosphere, let's say like Earth, it would still be tremendously hot. In fact, it would be hotter because of the greenhouse effect. And on that kind of planet, we wouldn't expect liquid water to be able to be maintained. On the other hand, if you're too far from the star, we wouldn't expect liquid water to be on the planet because it's too cold. Obviously, water freezes. So we want to be in the Goldilocks zone, some people call it, or the habitable zone, which is being in a temperate region where you have water vapor on the planet and the atmosphere, also ice, but huge amounts of water are actually liquid, like Earth's oceans. But there are some reasons to think that this isn't the best way to conceptualize finding habitable planets. For one, we talked about Europa, which is actually a moon of Jupiter. And Europa's surface is very cold. It has tons of water, but the water is frozen on the surface. It's frozen solid, but underneath the water, we think that there's a giant liquid ocean of water because of tidal forces. And therefore, we should be open-minded when searching for life outside Earth. But in any case, I just want you to know that this is one of the main ideas that people think about when they try to find habitable exoplanets. If you want to keep up with the exoplanets that have been discovered, you can go to exoplanets.nasa.gov. And this is where you can get the updated numbers. And as I said, I'll put the updated numbers in the comment section. I want to talk very briefly about how we find exoplanets. Don't think I have a blurb about that. I'm sorry about that. The blurb about this is actually in another lecture, but I want to mention it here briefly for the sake of completeness. The main way we find exoplanets is by what we call the transit method. This is a little bit hard for me to draw, but the idea is that, let's say you have a star. I'm going to draw a red star. By the way, it turns out that a huge number of stars are actually red dwarfs. So this is actually a pretty realistic scenario that I'm drawing here. Here's Earth. Obviously, it would be way farther away, but nonetheless, this is the exoplanet in question here. The idea is that this star is emitting light, and this light we can see, which is how we know the star is there. And if something were to get in between the star and us, it would block the light. If there happens to be an exoplanet orbiting this star that passes in between us and the star on a regular basis, then the amount of light that we will get from this star will dip. It's not going to dip by a huge amount, because planets generally are pretty small. There are exceptions to this, but there are giants out there. But generally speaking, the Earth, for example, would produce a very small dip. If this is the amount of light we're getting from the star, there might be a very tiny dip during a certain period of time. That period of time is going to correspond to the time it takes the planet to transit across the surface, to move. It's the best way of putting this, to move from left to right. So suppose you're staring at the star. We should never use left to right in space, right? But suppose you're staring at the star in a telescope. From our perspective, we have left and right. The planet, is going to transit across, appear to transit across the star from left to right. And the time it takes the planet to do that will be this time here. And this should be a regular interval, because we would expect the star to have a regular period. It will have a regular period of rotation, just like Earth takes the same amount of time to orbit the sun every year, which is 1 year. In any case, this is called the transit method, and this is the primary method by which we find exoplanets. I want to also talk about the habitable zone in somewhat more detail. This is a nice slide which depicts the mass of different planets, the mass of different stars, the mass of the host star versus the distance of the star, and then we have various planets that are plotted on this diagram. For example, the sun is here in the center. All of the planets in our solar system have the same sun, obviously, so the mass of the star associated with our solar system is just that of the sun. It's constant. So all of our planets are oriented along a horizontal line, but there are different distances from the sun, obviously. The Earth is here, and then we have the gaseous planets, and then we have the two inner planets with respect to Earth, Mercury and Venus, and then we have Mars here. And this green region is roughly the habitable zone that I was talking about. And then we have other planets here. These are exoplanets. And you can see that quite a few of the exoplanets are actually in the habitable zone. Now, the habitable zone gets closer to the star as we go down in mass, as the star goes down in mass. And the reason is that very low mass stars, like red dwarfs, don't put out a lot of light. And therefore, in order to have liquid water, you have to be closer to the star. On the other hand, if you're orbiting a blue giant, then you better be far from the star, because blue giants are tremendously hot. So that's the reason why this green habitable zone is of different distances for different stars. And you can see that some of these planets are actually right smack dab in the middle of the habitable zone. Now, I do want to give a word of warning here, which is that being in the habitable zone does not make you habitable. For example, it depends on how you define the habitable zone, but Mars and possibly Venus are within the habitable zone. This is one way of defining it. This is the optimistic and conservative habitable zone. Again, I should say this is just a concept that we have that we define because we think it's useful for finding habitable planets. And Venus we think is a little bit inside the habitable zone, which should mean it's a bit too hot. Now, Venus is way too hot, and that's because it has a very thick atmosphere. If Venus had an atmosphere that was like that of Mars, it would be much cooler. It might have similar temperatures to Earth, for example. So it's not just the distance that affects the temperature of the surface of the planet. Mars, for example, is inside the habitable zone, but Mars has a very thin atmosphere and it's not habitable for human life or pretty much any other life that we know of. Therefore, if we look at all these planets here which are in the habitable zone, we can't say, okay, so this planet here very likely has life because it's in the habitable zone, because we don't know what the atmosphere of the planet is, if it has one. It turns out that finding the atmospheric conditions of exoplanets is very hard because you can't really take a picture of them. They're too dim and too far away. We do have some information about the atmospheres of exoplanets, but at the moment the technology we have to do that limits our ability. Very lastly, in this video, I want to talk about one particular system which is very interesting. We don't have too much more time in this video, so I'll just make this very brief. But there's one system in particular which was in the news a couple years ago. In 2017, a total of 7 planets, by 2017 I should say, a total of 7 planets have been discovered orbiting the TRAPPIST-1 star. They all orbit nearly circularly, and the TRAPPIST-1 star is an M-type red dwarf. As I mentioned, this is actually very common in the solar system. All the planets orbit within about 1/16th of an astronomical unit. They're very close to the host planet, but the host planet emits very little light. And that means that some of them are in the habitable zone. We think around 3, estimating somewhat conservatively. Here are the planets. These are artists' conceptions of the planets. By the way, we don't have pictures of these planets, but these are the artists' or an artist's conception of the planets. We have various information about the radius, the mass, the surface gravity, orbital period, etc. listed here. And then we have the 4 terrestrial planets from our own solar system listed below. And you can see that some of the planets are not only very likely in the habitable zone of this TRAPPIST-1 star, but also very Earth-like. You can read about the TRAPPIST-1 system if you like, and I encourage you to read about whatever interests you, including exoplanets. But I would like you to watch this video as well. This video here is about the TRAPPIST-1 system, but I'm going to have you watch it. It's about 3.5 minutes long. I will post this to Blackboard. So please stop here and watch this video from NASA. And that's it for the lecture. In this lecture, we talked about the formation of planetary systems. I mentioned that planetary systems form, we believe, according to what's called the nebular theory, which means that they form from large clouds of gas and dust called nebulae. These contract under their own gravity, and as they contract, the moment of inertia of the cloud, or the part of the cloud that contracts, decreases, and as the moment of inertia decreases, the angular velocity increases, and this explains why our solar system is rotating. This also explains why it is shaped like a pancake. This tends to happen for objects that are rotating around, like pizza dough. And then we talked about the differentiation of the solar system. Thank you for watching this video, and I will talk to you in another one.